It is. I don't think it's become quite popular. I don't think it's really widely used yet, though. Okay, it's called SHAP. All right, I'm going to provide you a link to it.
Okay.
All right, it's basically a way for understanding the output of different types of machine learning models, particularly ones that are nonlinear. Okay, and so maybe are fairly difficult to interpret in different ways. Okay, so if you recall something like a random forest, it's a bunch of different decision trees and things like that. It would be difficult to maybe understand exactly what goes into the model and what its output are, simply because it doesn't really lend itself to interpretability the same way something like linear regression might. We have like a coefficient, you can draw a line through it. All right. So in any event, SHAP is basically a way of taking any sort of ML model, all right, and then being able to take all the individual columns and then break them down by their unique contributions, both for the entire data set, both for the entire data set, as well as for an individual sample. Okay. So the idea here, we're just going to go ahead and just kind of take a look at what it actually does or what it means. All right, so let's go into the notebook. I'm going to share my screen. As soon as I can find it. Okay, present. All right, can you see?
Yes.
Okay, all right, so the idea here, one thing you would need to do here, all right, you need to go ahead and then install SHAP. So I would say inside the notebook, do something like this, pip install SHAP. Hopefully, sometimes the installation can be a little finicky. So hopefully, if we're lucky, it will kind of go without a hiccup, and we'll be good. Okay, let me know if you run it and you're able to do it without getting any sort of interruptions or problems.
Just waiting for it to run.
Yeah, sure. Yeah, it'll probably run for a little while.
All right, I'm good.
Okay, all right, sounds good. You might want to try one more thing too. Are you on an Apple or a Windows computer, Ed?
I'm on Windows.
Windows? Okay, all right. So a couple other things too. A few of the things that are probably not going to be installed automatically. So try this. Pip install XGBoost.
I already got that one.
Okay, all right.
We're in the folders too.
Okay, all right, even better. And then the other one here, all right, is category encoders. So if you do this.
I got that one too.
Okay, all right, great. All right, so you're all set then. No problems there. All right, so you then go ahead. If you run this cell, this is just going to import a bunch of libraries and then read in the data. All right. Some of these, I'd imagine, are somewhat familiar, but maybe a few other ones are not. If you have questions, just feel free to let me know.
Okay.
All right. So take a look over here, next cell, okay? We are just sampling in the data right over here. It's 4.5 million rows, and depending on someone's computer, that could be a little bit much. So just to make this run a little bit more smoothly, about 250,000 rows. And so what we're doing then is we are declaring X and Y afterwards, and then create training and test sets. One thing here to take a look at, this data set, if you want, okay, again, is basically a collection of a bunch of police stops. All right. And so what it does is it logs the city someone lives in, their age, their ethnicity, their sex. Here you have some results of the outcome. So whether or not an arrest was made, if they found contraband, if they searched someone, and then also here you have the reason they were pulled over. Okay. If they were searched, what the reason was. Okay. And then also, if they were searched right over here, individual columns right over here in terms of why a police officer may have went ahead and then searched them. And then over here, you have some aspects about the dates, okay, in terms of what hour of the day of the week, quarter, things like that, okay. So the idea then, this is actually a pretty comprehensive data set for just kind of taking a bunch of things in terms of why someone was pulled over or what they did during a police stop and what kind of outcome happened as a result of it, all right. So that's what we're going to do here. And so the idea then, we're going to declare X and Y, okay, to basically study, all right, what might contribute to someone being searched, all right? So here we have the columns, right? So city, age, race, sex, reason for stop, hour, day, week, and quarter, all right? One thing here, all right, some of these columns may have occurred after someone was searched, okay? So for example, typically, obviously, an arrest, right, would have happened after someone was searched, or whether or not someone found contraband. You can only find that out by searching someone. So not every single column was included, okay? But basically here, the ones that would have contributed to whether or not a search was conducted at the time someone was pulled over, all right? So we're not including every single thing inside of X, just what would have come before someone would have been searched. So we're taking that, splitting it up into training and tests. All right. Here, previous workshops, we talked about gradient boosting. Okay, so here what we're doing, right, is just initializing the model. Okay, putting the encoders into a pipeline. All right, and then calling fit and transform over here, and then finally fitting the model. Let's go ahead and run. Okay, it'll take a little while. Okay, so now the idea then, okay, okay, the idea then is once you're done fitting your model, you can basically load that, okay, into SHAP. All right, and so SHAP is basically a way you can sort of think of it as being a universal model explainer. Okay, meaning you could take anything like a random forest or a gradient boosted model or a neural network or something else. Okay, and then SHAP can basically go ahead and then assign a numeric value to every single column's contributions to a prediction, right? Both at the level of an individual sample and also across the entire data set. So what that means, all right, if you run this line right over here, all right, it'll take a while to go ahead and run, okay? All right. Okay, so probably the most important thing over here, okay, is this variable over here called SHAP values, okay? So these are literally the actual contributions for each column for the model for every single sample. All right, so what this means then, if you look at this, right, next cell. All right, so this is a large array for basically every single data point. If you look at over here for 0, okay, right over here, all right. So if you were to kind of go ahead, okay, take the pipe, pick proba, okay, for the very, very first sample. excuse me, it would be mod, sorry, mod, not pipe. All right, so you can see here, okay, the probability, okay, of something being yes, okay, of someone being searched over here is about 14%. Okay, so basically here, what this array tells you, okay, is for each of the individual columns inside the data set, all right, this is how much each one contributes to this final value that you see over here like this. Okay, and so if you wanted to, they would actually add up, okay, to this value right over here. Okay. All right, so some things like the city where they lived in may have been positive contributors to whether or not they would have been arrested. Other things would have been negative, okay, depending on whatever characteristics are important for that. And so if you did that, okay, this would basically then go ahead and then break it down for basically every single sample in the data set. All right, so the idea then is you can take a look at these values and then you can study them both for the data set as a whole. So maybe, you know, how much does something like ethnicity or age, you know, contribute to someone's, you know, probability of being arrested or searched, but also for an individual sample. Okay, so if you have a single prediction that your model is making, you can kind of go ahead and then break it down into its individual parts. Okay. Other thing here, the SHAP will go ahead and compute once you go ahead and do something like this. All right, something called the expected value. Okay, so this number right over here is basically just the baseline. Okay, the baseline prediction that the model is going to go ahead and make. And then these are pretty much the contributions of each of the individual columns. All right, and so it is this right over here, okay, added up to this right over here, okay, would give you this number right over there. Okay. I know at least previously with me and maybe other spots, you know, you basically have discovered linear regression.
Mm-hmm.
Yeah, so in a lot of ways, this kind of allows a nonlinear model to be interpreted in a manner that's kind of similar to linear regression, where you have coefficients for each individual column, and then you can kind of add them up to kind of get the contribution to your final prediction.
Interesting.
Okay, so even though if you have a model that's actually not linear or otherwise is not very interpretable. And so this is big because a lot of times, you know, people, typically the most popular ML models are fairly high powered and they don't really have clear explanations for why they might produce a prediction. But this kind of gives you a way just to kind of really clearly take a model's output and then map it back to every single unique value inside your data set. Okay. And then something that's useful about SHAP in particular is it comes with a really nice graphing library for kind of looking at patterns inside your data. And so it's actually quite well done. So, so questions so far?
No.
Okay, all right.
Impressed actually with this tool.
I'm sorry?
I'm impressed with SHAP though. Honestly.
Yeah, no, it's actually, it's pretty nifty. It was developed a couple years ago. It's become quite popular for people who like to use these sorts of things. You haven't seen the graphs yet, Ed, but to be able to kind of like think about something like a random forest, like linear regression, is actually really convenient in a lot of different ways. Okay. So in any event, okay, SHAP is useful also because it comes with a lot of really useful graphing libraries out of the box that look really nice. Okay. This is basically the average SHAP value, okay, for every single column across the entire data set. You can sort of think of this as being something like a global coefficient, okay, for each column inside your model. This is useful, okay, but maybe it's not that different from other things you might be able to get, like feature importance or something like that, okay, but just overall how you might rank each column in terms of contributing to the outcome. Okay, and you can see over here, right, reason for stop, your maleness, and your age kind of dominate overall concern, and you can have some other considerations over here. Okay, so this is just the average value for every single column. Okay, what's typically more useful for SHAP, okay, is you can actually break these things down across all of your samples. Okay, so for example, All right. This is a single bar chart, okay, for each column in the data set that kind of gives you like one lump sum average value, okay. This one tells you how each of these values are distributed, okay. So the idea here, okay, the larger one of these values are, okay, the more it will contribute, okay, to your chances of getting searched. Okay, so at this point, right, if the value for SHAP is basically right around 0, that pretty much means it has basically no impact. Okay, the larger you go to the right over here, all right, the more likely it is to contribute to your chance of being searched, and the farther you go to the left over here, the more the opposite over in this direction. Okay, so this basically then, if you look at this one single number right over here, 0.51, right, for the reason for stop. Okay, in terms of how it contributes to the final outcome. Okay, you can see here that 0.51 is actually broken down in some pretty clumpy ways. All right, more likely than not, what you're seeing okay, there are about 5 or 6 different unique values for reason for stop. And so more than likely, each of these different clusters, okay, probably represents each of these different values over here, okay? So I would imagine something like here probably represents drunk driving, okay? Something over here to the left, we kind of have like a big bulge of maybe it modestly, basically decreases your chances of being searched, but not dramatically so. It's probably something like speeding, or running a red light, where it's kind of a mundane reason for being pulled over. And so therefore, there's not a particular reason, you might basically pose a threat or be a menace to society, even though the police have reason to go ahead and then pull you over, okay? Likewise, if you go over here for something like this, whether or not you're male, okay? So this group right over here, right, are probably the men, okay? Because all else being equal, men get searched more than women do, okay? Over here, okay, you can see is basically, the non-men or the females, okay? We can see over here, right? So if you're a male, okay, basically the way of being a man contributes to your chance of being searched is somewhat consistent, okay? It's very, very positive, okay? And also kind of falls in a consistent range. However, though, if you're female, okay, how that decreases your chances of being searched is actually quite variable. Okay, we can kind of see over here, right? The spread of values for non-males, is much larger than it is for being male. Okay, and again, you can kind of see this in different spots, right? With something like age, you can kind of see like there are big bulges right over here. Okay. Likewise, maybe if you look at something like city, okay, it looks like there's probably one city, okay, which really consistently adds, okay, to your chances of being searched. But among the other cities, there's kind of like this long tail, okay, and they kind of gradually decrease your chances in different ways. But in any event, it's kind of a useful way to kind of see how a lump sum aggregate number can get deconstructed into a bunch of smaller values. Okay. We're going to talk about this more here, but I'm happy to answer questions about maybe what a chart like this might mean or something like that.
I'm good. I'm wondering if this is useful when you're doing regression but non, classification problems.
Yeah. You're right. This so basically if you're doing the standard regression.
Okay.
Yeah, no, this actually this works both for classification and regression.
Okay.
In fact, as far as I know, Ed, I'm pretty sure the charts basically work exactly the same too.
Yeah.
Okay. I don't actually think there's a meaningful difference. Okay. Okay. All right. Let's take a look at a couple other ones here. Okay. Another useful thing here that you can do with SHAP, all right, is you can go ahead and then isolate, all right, how a single, basically how SHAP values for a single column, okay, change with different values. Okay, so in this case, subject sex male, okay, is right. Just it's either going to be 0 or 1. Okay, so we can kind of see over here, right, for the values that were 1, basically for the men in the data set. Okay, you can kind of see how the values are distributed. Okay, so they're basically clustered right around something like 0.3. Okay, and then right for the people who are not male, okay, which is 0, you can see over here, right, they kind of span from -0.4 to about -1.1. Same thing, this chart in many ways tells you something that's maybe somewhat similar to this one, okay, because it's actually kind of conveying the same information, okay. One thing, though, that it does a little bit different is when you call something like this, it will actually calculate, okay, which column in your data set actually has the largest interaction, okay, with this particular column over here. So in this case, all right, if you're male, all right, the actual largest like mitigating or sort of interacting column, okay, with your outcomes, okay, is whether or not you're black. Okay, and so here they're going ahead, they're colored, okay. Where like, you know, if you're positive, if you're 1 for that column, it's 1. If it's 0, it's going to be blue right over here. So therefore, among the distributions, right, of the SHAP values for men and women, you can also see how they're broken down by this column. And this one is basically computed for you automatically to kind of tell you which one has the biggest interaction effect, okay, with one versus the other. And then you can basically kind of go ahead and kind of get the breakdown between the two for each of them. All right. Another example of this. All right. This is a categorical value, so it's 0, 1. Okay. This is continuous. All right. And so here we're basically saying how your chances of being searched, okay, change with age. All right. And so in this case, all right, probably not surprisingly, okay, young people, okay, get searched more often than older people. And so in this case, you can actually see the effect, okay, of age on your chance of being searched is basically linear. Okay, it looks like there are probably some outliers or misentered data right over here. Okay, but by and large, you can almost just kind of draw a straight line, okay, right through this chart here. And so basically, there's like a very, very strong linear pattern in terms of how getting older decreases your chances of being searched. Okay, and so same thing over here, okay, among people on your age, the strongest interacting feature with that is whether or not you're male or female. And so same thing over here, you'll see them colored appropriately. Okay. So basically what this means is if you're, depending on how old you are, the next most important factor that'll modify your chances of a particular outcome is whether or not you're male or female. Okay, and so presumably, you know, people who are young and male in particular probably have a very high chance of being searched, you know, compared to people who are female. That would be my guess. But in any event, it allows you to kind of see a global pattern, but kind of broken down into each of the individual data points inside your model. Okay, so just kind of collectively, I think it's pretty informative for me what kind of patterns your model's kind of finding out inside your data. Okay, so everything we're seeing right over here, Ed, okay, is basically a global pattern for your entire data set. Okay, so this is basically what we found for all 250,000 rows, okay, that we looked at over here. All right. Also, if you would like, all right, you can go ahead, all right, and also calculate SHAP values and put them into charts for individual predictions. Okay. So in this case, for the very, very first sample in our data set, okay, this was the final prediction right over here. Okay, which is actually expressed as log odds, not raw probability. Okay, this is the baseline value right over here, And then you can basically see how each individual value in the actual sample itself contributed to the final outcome. Okay, so in this case, if you were to look at the first row of X, actually, let me try this. DF, iLoc, since this is randomly sampled. Okay, you can see here the fact that this person was 57, okay, heavily contributed to them being unlikely to be arrested, or rather to be searched, okay? And again, you can kind of see that over here, right? That puts them about over here in this chart like that. Okay, next biggest thing, right, is the reason they were pulled over. They were speeding, you know, so speeding is probably a fairly harmless reason for getting pulled over for something. It doesn't really signal any sort of, you know, particular danger. People who get pulled over for speeding are probably not searched very often. They're probably just given tickets. Okay, so this is the next biggest thing. Okay, likewise, okay, you know, if you're black or not is an important, you know, predicting factor for whether or not you'll be searched. So you can see over here, this was 0. Okay, so therefore it pushed it in this direction. However, though, this person was male. Okay, and so therefore we can see, right, being male added this much right over here. Okay, and then you have all the other things as well. All right, the idea, though, it typically, though, gives you a really nice way to visualize basically what a model is seeing for a particular sample, as well as an entire data set. Typically, especially I find if you're deploying something, okay, and using something in production that's being used for real-time predictions, being able to decompose something into its individual parts is, I think, a pretty big boon.
Yeah, interesting.
And same thing too, this is kind of like a pretty highly powered nonlinear model, right? And so these values would actually change for each individual sample that you gave it. You know, so if you look at the next person, okay, it looks like we have a 49-year-old female who lives in a relatively safe city, who was pulled over in the morning. You know, and so on and so forth, okay? And so you can kind of go on through it, but basically it's the same basic idea. You can kind of get real-time inference on a single sample as it comes up in a way that's pretty interpretable. And this is for a technique that up until this point was probably considered to be a black box technique. You know, things like that would be difficult to understand. So for tree-based models, this has become a really popular way for understanding them. All right, and then final plot over here, if we wanted. Okay, it's really just kind of a slightly different way of looking at this one. So this is the waterfall chart. This over here is called a force plot. It basically connotes the same information. Okay, like all the values over here are about the same. But same thing though, this time though, you kind of start with the final prediction over here. And then you kind of have on the left and the right-hand side what contributes in each direction. Okay, and you can see overall, right? We started over here as kind of the baseline expectation. And then, right, because this is an older female, you know, who probably got pulled over for something fairly harmless, okay, in the morning in a relatively safe area, you know, it basically pushes the probability of her being searched down over here at this level right over here like that. Okay, and obviously you can kind of pull it, play around with this in different ways, but collectively, it's a really useful way for being able to study the output of your model. It also makes nonlinear models a lot more usable in various ways. Okay, so personally, I have found this pretty helpful in a variety of contexts, and it definitely expands the type of techniques you can use to study your data and to be able to understand what they're telling you as a result. All right, so that stops the walkthrough. Okay, same thing. I'm happy to answer any questions.
Well, I have no questions so far.
Okay, all right.
I'm still shocked with this.
Yeah, no, it's the plots look great, and then it's extremely informative too, in terms of finding patterns and that kind of thing. So, yeah. So feel free if you have a question or something like that. I didn't have a formal lab or anything like that, but I probably what I was going to do is, if anyone wants to stick around, obviously we have a small class right now, Ed, but probably we would just take a second data set, okay? We can make it regression and just kind of recreate some of the same charts, just to kind of get a bit of practice using it.
Okay.
Okay. So if you want to do that, that's awesome. We can kind of go and stick around. I'll kind of put everything on pause for a little bit and check back in. Obviously, it's your call. If you have other things to do in the evening, I won't hold it against you.
Okay. Well, at least if you could get send me the data.
Yeah. I'll go ahead. I'll post the data set. We'll probably do something smaller, just kind of get a chance to go and work, and then and then we can take a little bit of time if you want to kind of go ahead and work through some of it and just kind of recreate some of the stuff to make sure you have a handle on how you kind of get certain things to render and that kind of stuff.
Okay.
1 minute here, okay?
All right.
All right. If you don't mind, I'm probably just going to use one of the data sets for class. All right. You mentioned regression, right?
Mm-hmm.
Okay. All right. Let's go ahead and take a quick look. Okay, this is a smaller data set that should be, I think, pretty easy to go ahead and deal with. So it's posted in the Slack channel. All right, and so the idea is, okay, yes, if you're going to stick around, we can probably take maybe 30 to 40 minutes,
Okay.
just to kind of take this particular, a different data set, kind of put it through the paces. And just so you can kind of recreate some of the same stuff and just make sure you're clear on sort of the details and what it tells you. Okay. And again, obviously, since it's just the two of us now, if you want to go and do that now, that's awesome. And we can kind of go ahead and then reconvene here in about a half hour.
Okay.
If that's good with you, we'll go ahead and do that. And then if you want to go ahead and do something else, that's fine too.
Okay. Yeah, I think we're good. I'm gonna play with this and let's see.
Okay. So shall we maybe in like 30 minutes or so?
Okay.
Okay. All right. Sounds good. All right. So I'm going to stop recording now, and then we'll touch base then and go from there.
Okay. Perfect.
Beautiful. Hey, Edward, how's it going?
Oh, good. I'm all set.
Good, good. Any questions?
No,
Okay.
I was actually testing with other plots, and
I'm sorry?
I was testing other plots, and
Yeah, yeah. Actually, the plots are pretty informative.
Mhm.
They actually tell you a lot about what's happening inside of a model. So it's, yeah, I think it's actually pretty good stuff. That is basically what we have for the evening then, sir.
Okay.
Yeah. Again, if you have any additional questions or things like that, I'm happy to go ahead and answer any questions. But the idea is to kind of take a data set and just kind of test out some of the charts and things like that and get them to work.
This is pretty cool, Jonathan. Now I want to apply it to all my.
Yeah, no, it's a good way moving forward to kind of interpret what you're doing, and things like that, and communicate stuff. So also, I think at this point, pretty contemporary, Edwin. So I think it's actually outside the vanguard, like most kind of like data science education, things like that. So I think you're putting yourself in some, I wouldn't say exclusive company, but definitely pretty close, like the frontier of like like model interpretability.
Nice. Well, I don't have any questions.
Hey,
I want to play with this new toy.
yeah, for sure. I think we're gonna have one more workshop on it in a couple of weeks, and then we'll move on to a different topic.
Okay. What
Beautiful.
are we going to do next?
I'm sorry?
What are we going to do next?
I think what we're gonna do is I would like to be able to keep doing this more regularly. And so probably what we'll do for a while is just have meetings where we'll be given data sets, and we'll just kind of work on them for a little bit, maybe individually or in teams, and kind of do that for a little bit. And then once I have time to kind of put together a new topic, go to that.
Okay. Nice.
Mm-hmm. Cool. All right. Well, I will talk to you later, sir.
All right. Thanks for everything.
No problem. Bye-bye.
All right. Bye-bye.